Okay, so ID 6. So we've got an equation given to us, and we want to show that we can solve for z as a function of x and y. And this is right down the pipe exactly what the implicit function theorem does. So we're going to look at this algebra. So we've got this function f of x, y, z is, all right, let's e to the z times x squared plus y squared. Yeah, and then plus e to the 3z. And this needs to equal to 5, so we're looking at a level set of this function. So this is the function that we're going to be taking the partial of with respect to whatever variable we want to show we can solve for. And in here I want to show that I can solve for z as a function of x and y, so I'm going to consider the partial of f with respect to z. Right? Okay, partial with respect to z of that is, well, it's this exponential, but then, yeah, okay, so e to the z times x squared plus y squared, and then times the derivative of this exponent with respect to z, which is x squared plus y squared. Okay, plus, now what's the partial of that with respect to z? Well, that's no problem, it's 3e to the 3z. And the question is this necessarily known, well, let's see, let's do it like that. Is this necessarily known to be not 0? And I claim there's no way that could possibly equal to 0. So now we have to think that through. You know, why is it that I assert this can never be equal to 0? Well, because this is never equal to 0. This is always positive. Right? And this, now this could be 0 because x and y could both be 0, so this term could end up being 0, but this can't. So, and furthermore, this is always non-negative. So it's not like these terms could ever cancel. This is always positive, this is never negative, therefore there's no way this could ever add up to 0. So this partial derivative is never equal to 0. Now you got to write that up in words a little bit. You know, you have to argue that, you know, this first term is never negative, the second term is always positive, etc.
So you can write that in sentences.
Yeah, just write it in sentences. Yeah, absolutely. Yeah, absolutely. Yeah, I mean, you know, keep in mind, by the way, math is about reasoning, and reasoning sometimes it's algebra. I mean, algebra is a great kind of reasoning because there's no arguing, there's no. You don't have to worry about phrasing and stuff. You just do your algebra, you do it right. There's nothing to argue about, right? Unless you do algebra wrong. But sometimes reasoning is just words. And as long as it's valid, then that's fine. Yep. That makes sense to everybody? Okay. So now having done that, so I say we can view z as being a function of x and y. So that's good news. And now let's go on to the next part of the problem of actually finding these partial derivatives. And I'll do one of them, and I'll let you guys do the other ones, or the other one. So I'll compute partial of z with respect to x. So I'm going to start with my original equation. That's my original equation, and I know that I can view z as a function of x and y. So I'm going to, with this point of view that z is a function of x and y, I'm now going to take the partial of that whole thing with respect to x. And the reason I want to take the partial with respect to x is because I know that altogether I'm going to get 0. And I know that in viewing z as a function of x and y, if I take the x partial of this whole thing, then as I go through and use the chain rule, the partial of z with respect to x is going to show up. And then I can just solve for it. Is that okay with everybody? So, I mean, there's a strategic choice as to why I'm going to take that x partial. So, now be very careful when you do this, because we are now viewing z as a function of x and y. So when we take the x partial of this, we're going to have the exponential. Now I have to multiply by the partial with respect to x of z times x squared plus y squared. And this is where we have to be kind of careful. and of course there's another term over there. But what is the partial with respect to x of this? Well, z is a function of x and y. X squared plus y squared, also a function of x and y. So I have a product here. So I've got to use the product rule. In fact, let me pause. Well, I claim we'll have to use the product rule here, but let's get the rest of the algebra of this equation down, and then we'll go back and deal with that. So, okay, what's the x partial of e to the 3z? Well, it's e to the 3z. Now I've got to multiply by the partial of 3z with respect to x. Well, that's 3 partial z with respect to x. Partial of 5, of course, is 0. Okay. So moving along. What do we do with this? Well, I claim that we get, first I take the partial of the first term, so I have partial z with respect to x. Second term stays there. Second factor stays there. Now I have then the first factor, z, and now I've got to take the partial of x squared plus y squared with respect to x, and that's just 2x. So here I've expanded out the product rule as it applies to this. We okay? Everybody happy with that? Yes?
So I think my question is, when we did partials of couple sections before, we treated any variable that's not the variable in interest to be a constant.
Yes.
But here you decide to treat z as a function of x, but not y.
No, z is a function of both x and y. And so everything in here, in this expression, everything's viewed as a function of x and y. And so when I take the partial with respect to x, what that means is we're going to view all the other variables, namely just y, as being constant. X is going to be the variable that we're going to be taking the derivative with respect to. Z is no longer a variable. Z is a function. Right? So that's why we don't treat it like a constant. It's not a constant. It's not even a variable. It's a function. Does that make sense? Yeah, it is very confusing. And what always used to weird me out on these kinds of problems is that here I was taking a derivative with a partial with respect to z, and it kind of felt like, well, that means z is an input variable. How can I view z as an output variable here? And what was happening is I didn't really realize, this is before I had seen the implicit function theorem, I had just seen implicit differentiation. I was like, well, dude, you're cheating. You're sometimes viewing it as an input, sometimes viewing it as an output. That doesn't seem right. And, well, no, it's perfectly reasonable because of the implicit function theorem. Yeah, does that all make sense? Yeah. So the implicit function theorem is what allows us to do this. Yeah. Okay, great question. Thanks for that. Okay, so moving along. So this is what that turns into. Now we have plus e to the 3z times 3 partial z with respect to x equals 0. And now what? And by the way, this algebra looks just nasty. Great news, nasty though it is always, and it will always be, very simple in terms of the things that we care about, the things that we want to solve for. Namely, partial z with respect to x will always be a linear factor. You're never going to have sine of the partial derivative you're looking for, or e to the power of the partial derivative you're looking for. It'll also always be just a linear factor. So this is just a matter of sort of collecting terms and moving some to the other side, dividing, etc. And I claim partial z with respect to x is, well, let's see here. This term goes over to the other side, so we get 2xz e to the z x squared plus y squared. And now we divide by the collected factors that multiply by the partial of z with respect to x. And that is x squared plus y squared e to the power of z x squared plus y squared. That was that there. And then this here, 3 e to the 3z. There you go. One thing you might try to convince yourself of, and you can do this if you'd like, 6 one way, half a dozen another, is I claim that if you're viewing if you have f of x, y, z equals a constant, and if you view z as being a function of x and y, then the partial of z with respect to x is the negative of the partial of your original f with respect to x divided by the partial of your original f with respect to z. And you can check it. That's exactly what happened in the previous example. I tend to not. I don't want to really encourage students to do this because I think very often students just take this as kind of the magic formula. This is just what you do, and don't really understand that there's a process involved there. But this is something that will work. Yeah. Okay. Any questions about this problem? Yeah.
Can you explain again what? So I missed that last part.
This here?
Just the dz dx. So
yeah.
That is just like the formula that we're not supposed to really use, but I mean like it's equal to df dx.
Yeah, that's right. And don't forget the minus sign here. And see, what's confusing about this for a lot of students is a lot of students say, well, wait a minute, why is the minus sign? It's like these df's should sort of cancel, and here we have a denominator that should go up to the numerator. This should be that without the minus sign. But that's just not how it works, right? Where this comes from is if you look at your original thing, let me show you where it comes from. If you look at that equation, what we've got is f of, well, let's see, how do I want to do this? Yeah, let me just, fine. Let's just take the partial of this whole thing with respect to x. Let's see what happens. Now keep in mind we're viewing this as a function of x and y. So what's the partial of this whole thing with respect to x? Well, this left-hand side depends on several different variables. It depends on x, y, and z. So I'm going to take the partial of f with respect to x times the partial of x with respect to x plus the partial of f with respect to y times the partial of y with respect to x plus the partial of f with respect to z times the partial of z with respect to x. That all adds up to 0. Now, what do all these things in here mean? Keep in mind, everything in here is a function of x and y. We're taking a partial with respect to x, which means we're going to view y as being a constant, and if y is a constant, that's 0. And, of course, this is just 1, and that's what we're trying to solve for. And if you just then solve in this equation for the thing that you want, you get that equation.
So it's just a shortcut way to find dz.
Yep. Yep. So pro and a con, it's important to make sure you understand where this equation comes from. The negative, the con, I shouldn't say the negative. Would be an ugly pun, right? The con is that you have to make sure that you get the right formula. Now, in this case, you could just memorize this, sure, but what if you're not solving for the partial of z with respect to x? What if you're solving for the partial of x with respect to y? What if there's multiple different variables running? Maybe it's not just x, y, and z. Maybe it's x1, x2, and z. And you just have to make sure you remember that you interpret the formula correctly. What's nice about doing problems this way is you don't have to remember anything, right? You have to remember the implicit function theorem. Got to check the right thing, right, to make sure that you can view it as a function. But then everything down here, you're not memorizing anything. You're just interpreting as appropriate, doing the algebra, you get your answer. Yeah.
So if for the part below where you have dx dx, is that just because it's only going like in our little chart thing of variables, there's only two sets. So you're going dx is like directly related.
What I was interpreting here is that we have x, y, and z that go into this function f, and then I was viewing everything here as functions of x and y. And so I was taking then the partial of this f with respect to, so whatever this output is, let's call it w, taking the partial of that with respect to that. So sure, you take partials with respect to, you've got x, y, and z. F is a function of x, y, and z. That gives you these three partials here. But then in taking a partial with respect to x, this becomes a constant. Of course, these are equal. That means that that's a constant. And that means that when you're taking these partial derivatives, well, that's a constant that you're taking a derivative of. So that's why this one's 0. And this one's 1 because because this x is that. They're the same thing.
That's what I was
Yeah, okay, yeah. So they're the same thing, so that's 1. Yeah. Right. How we doing? Anybody else? So I'm going to let y'all do the y one, the partial with respect to y. It's very analogous, and I think you guys can probably do that. Okay, let me stop this recording.